My name is Knock Acker, and we have Christina Hammock speaking today about space, science, engineering on the Juno mission to Mars. Thank you.
Thank you. Actually, a mission to Jupiter, but we don't want to hear him try that again, so just let it go. Hi everyone, my name is Christina Hammock, and I'm new to Barrow. I just actually moved into town a couple weeks ago, and formerly to coming here, and I work at the NOAA facility here with Matt Maritson. Before I worked here and in other polar regions, I worked for a facility that had NASA grants to make space science instruments. So that's actually what I'm going to be talking about today, is my work in space science, instrumentation engineering. Just before I get started into the actual mission, I just want to talk a little bit about where I worked. The place was called the Applied Physics Lab, and it was a lab associated with Johns Hopkins University. And within that, the Applied Physics Lab, or APL, there's a large space department, and the space department gets NASA money to actually make instruments, and in some cases make the actual spacecrafts for NASA missions. And within the space department, my group was called the Space Science Instrumentation Group. So we focused on making the actual small little space gadgets that ride on the spacecraft that actually do the science of the missions. And I guess this slide really speaks to what I just said, but so our scientific instruments fly on both planetary probes and Earth satellite missions. And specifically within the instrumentations group, the types of instruments that I worked on were called particle detector instruments. And they have a lot of different applications and a lot of different types of space missions. We have explored new planets, so we've actually sent the first probe to Pluto and the first probe to orbit Mercury with a particle detector instrument. We study more of the cool stuff, the cool planets we've already seen a little bit of, like Jupiter. And then also we use particle detector instruments to study Earth. So we've got a few missions in the works that are going to be Earth orbiters. And I have highlighted Jupiter because obviously that's what I'm going to be talking about more today. So the mission that we have an instrument on right now is called the Juno mission to Jupiter. How many of you guys actually heard in August about this mission launching? Oh, awesome. That's great. Yeah, it was in the news a little bit if you were paying attention. Or if you're a geek. So basically, Juno is the name of NASA's latest mission to study Jupiter more in depth, and our instrument is actually on that mission right now, and our instrument is called JEDI. And the overarching scientific goals of the mission are basically to learn more about our solar system as a whole by studying Jupiter more in depth, because it's kind of an analog for the solar system development because it's such a large gas giant planet. And again, it launched just this past August, and it's not going to get to Jupiter, unfortunately, for 5 more years. So in 2016, we'll get to actually learn something. So first, a little bit about why we are going to Jupiter just in general. Why do we have this Juno mission? And this is just a quote straight off of the Juno website that I found with a couple examples of the things we're studying more in depth, because we've actually already visited Jupiter with previous planetary missions, but not as in depth as Juno is going to do. So what we want to look at is the core of the planet, whether it's got a solid planet core, its magnetic field, which is actually really interesting for a lot of reasons I'll talk about later. Jupiter's magnetic field and its magnetosphere is actually the largest thing in the entire solar system. And then also we're going to study kind of the composition of the planet, whether it's got water, ammonia, and then finally observe the planet's auroras. And again, that's highlighted because that's a specific thing within these scientific goals of the whole mission that our instrument addresses. Okay, so why do we care about auroras on other planets? Well, first I thought that I'd talk about how auroras work here at Earth. Did anyone see the awesome auroras this week here in Barrow? Yeah? Did any of you guys hear on the news some of the stuff that was going on with those, like in the rest of the world? What are some of the things does anyone know what auroras can cause to the Earth, like in practical terms, other than just making pretty lights?
Does this have something to do with the solar radiation that we get bombarded with?
Exactly, yep. So auroras are caused by solar radiation. Basically, the sun has these big solar flares and ejects these huge bodies of radiation. It's called a coronal mass ejection. And when those things hit our planet and hit our magnetosphere, they're actually ionized, and then they get trapped in our magnetic field, and they get accelerated back and forth along the magnetic field lines between the North and South Pole. And when that happens, and when those particles interact with the Earth's atmosphere, it actually generates these beautiful northern lights. And when we have really strong solar storms, it can actually interrupt power grids. It can stop communication satellites. A lot of satellites that are in orbit actually will have to reset themselves. They'll have to turn off and turn back on. So it actually has a lot of practical effects on our planet.
Question?
Yes?
Does that effect the same or different than like when a nuclear weapon goes off and you have one of those electromagnetic pulses?
I think the physics of it is the same, because the idea is that anytime you have large fluctuations in the electromagnetic fields, you induce voltages in electronics in various places that aren't normally there, and it can cause them to need to reset. So yeah, it's the same physical phenomenon at the end, but not obviously a different origin, but yeah. And then this is just a picture from space of where the auroras hit at the North Pole, typically. And then this is a picture that I took here in Barrow just a couple nights ago. So this whole phenomenon, studying how auroras affect, or how the magnetosphere interacts with the atmosphere and blah, 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 is all called space weather. And it's a big field right now in NASA. It's not really well understood. And instead of just studying it here at Earth, we wanted to use Jupiter as another test case to refine some of our models of the magnetosphere so we can understand more how to predict when these things are going to cause problems with our satellites and our power grids, and to be able to know when they're going to be bad or not so bad. So as I mentioned, Jupiter also has auroras. This is some really cool photography that was actually taken by the Hubble Space Telescope of the auroras on Jupiter. So I think this is really neat. So this is just a picture of what we're going to be studying. One really cool thing in this picture, do you see these 3 dots here? Okay, so those aren't just random dots. That's actually a signature in the aurora of Jupiter's moons. So what happens is the moons of Jupiter emit particles just because they have atmospheres and rocky cores and whatnot. And then because the magnetic field of Jupiter is so strong, those particles get ionized, and then they become trapped in the magnetic field of the planet, similar to how the solar wind does. But because there are these sort of point sources of particles, they end up making darker spots in the auroras. So Jupiter's auroras are not only as cool as Earth's auroras, they're even cooler, because you can actually learn about the moons of Jupiter by studying the auroras of Jupiter. Yes?
Moons or what's going on?
You know what, let me show you this movie, because I think this will help explain it. And that's a great question, because that's exactly what this movie is about. So, what happens is you get a moon, and it's just emitting particles because it has an atmosphere the same reason Earth does. Those particles then become ionized. They get their electrons ripped off by the radiation belts of Jupiter that are a result of its magnetic field. And then they become trapped in the magnetic field lines of Jupiter, and they basically, their signature of where that kind of source of particles is, an additional source more than just the normal ones, they actually bounce back and forth between the North and South Pole along the magnetic field lines, and then they cause little spots of extra auroras. So normally there's just kind of a nominal, normal amount of particles always trapped in the magnetic field of Jupiter and of Earth. And when those particles bounce back and forth between the North and South Pole along the field lines, they cause the aurora. But with Jupiter, you get these extra spots because you have this extra kind of source of particles. And then they kind of create this little signature dot in the auroras.
So with our moon?
Our magnetic field of the Earth is not strong enough to have this effect from our moon. Or else it would. It stands for the Jupiter Energetic Particle Detector Instrument. And again, it measures the charged atoms, and it also measures electrons that are trapped in Jupiter's magnetic field. And so these are the things that it studies by measuring that, or as I mentioned, the field itself. You can infer the strength of the field. You can infer the things that are contributing to the auroras. And also you can just get a general idea of the strength of the radiation belts themselves around Jupiter. And then in addition, because Jupiter is so cool, we have this added bonus of being able to do some geology interpretation of the moons. Okay, so just a little bit, just the physics of how this instrument works. It's kind of cool. In order to, I mentioned that we actually will have the ability to tell what these different ions are. So let's say, is it a ionized oxygen or an ionized sulfur, because that tells us a little bit about the moons. So in order to know that, we have to know both how fast the particle is going and its total energy. So we have a little speedometer in there. It's basically two detectors that sit a known distance apart from each other, and they have really, really precise timing. So we get one signal from the front one signal from the back one, and then we can tell how fast the particle is going. And then in addition, we get the total energy of the particle by basically absorbing the entire particle speed, stopping it in a substrate, and measuring basically how much damage it does in that substrate. And so you can kind of think about that as like taking a cue ball to break in the beginning of a pool game. You can tell how much energy you had hitting the cue ball by how much the grouped ball scatters. And then that allows us to not only determine the type of particle, but how many they are, and then what direction they're coming from. Any questions?
What's the word ionized?
So, thank you. Ionized basically means that you have a regular atom, and it's been hit by an electron or something else that has caused it to lose one of its electrons. So it's basically an atom with a charge. It's a charged particle. So you've heard of radiation being described as like, radiation from nuclear plants or something like that. And what that means is it's just any material that emits like electrons, which is a form of radiation, or in some cases alpha particles, which are little helium nucleuses and stuff. So ionized just means a normal atom, a normal everyday atom that's had an electron ripped off. So therefore it's subject to being influenced by magnetic fields. Good question. Anything else? Does that make sense? Are you lying? Okay, so now the rest of the talk is just going to be pictures. And basically what I'm going to do is take you cradle to grave of starting with my part in the instrument early on when we were building and designing it all the way through launch. So the making of a space gadget. The first thing, my sort of subsystem in the instrument was those detectors that I told you about that measure the total energy. These are pictures of them. They are made of silicon, and basically silicon is what's called a semiconductor, which means that when it absorbs a particle of radiation, a lot of electrons are released, and we collect all those electrons, we get a signal, and then we can tell the total energy of the particle. So these are the little detectors, and then that's the back of each detector has a little preamp, and then that sits inside the detector head. So this is the top of those detectors, and then this is the speedometer I was telling you about before. This is the front and the back detector. And then all these holes up here are what's called a collimator, and that just makes sure that all the radiation comes in at one incident angle. And then the rest of it, all this stuff here, are our 4 electronics boards. We make custom electronics for it so that it can be really, really ultra low power, and so that it can be really, really fast. So there's really high state-of-the-art power and state-of-the-art digital processing. And it all can withstand a lot of radiation. So.
What's the power source?
The power source is the solar panels of the instrument, or of the spacecraft.
Sorry?
The solar panels of the spacecraft. Yep. And that's why it's so important that it's low power. Yes.
The metal casing, is that aluminum or titanium?
No. Oh, I'm so glad you asked. It is copper tungsten.
I'm sorry?
It is copper tungsten, which is a material. It's not quite an alloy. It's somewhere in between an alloy and just raw material. And basically, we chose it because that thing is really, really heavy. That thing weighs like 16 pounds, and it's only about this big. And it's because of the intense radiation at Jupiter. We had to actually have something with a really high ability to stop radiation. So it was like, lead or that.
So it doesn't conduct electricity?
No, it does. This housing is actually conductive. Yeah, and we actually use it as a ground. So we tap into it as a ground from all of our boards.
And it's got a sustained temperatures that are just unbelievable.
Totally, and I'll talk about that later too. Yeah, even colder than Barrow. Yeah, I know. Actually, not much colder now that I think about it. Because we only have to specify it at like -50. Oh, that's Celsius. Anyway, it's
a little bit colder there.
But yeah. That's great. There are heaters on the spacecraft that regulate it to within our temperature specifications because the outdoor temperatures are much, much colder, but we regulate to within like -50 to like +60 or something Celsius. Okay, so once you've got your space gadget assembled, then you need to start to break it, or try to break it, because as was alluded to, we have a space environment out there that we need to make sure it can withstand. So what are some of the things that are different in space than in our lab here?
No
Extremes of heat.
That's right, no atmosphere, exactly. Yep, so
Hot and cold.
exactly, that's exactly right. There's no atmosphere, so it has to be able to operate in a vacuum, and it has to be able to withstand really extreme temperature cycles. So every single time we test our instrument, we have to put it into a high vacuum chamber. So it's a real pain. You can't just work with it on your lab bench and play around with it. So these are some of my colleagues putting it into a vacuum chamber. In this particular test, we were actually shooting it with electrons. We had to go to NASA. They have this huge electron gun, and we shot it with some electrons and saw how it responded while it was in the vacuum. And in fact, our instrument doesn't even work when it's not in a vacuum. So, so then this is a test that I was setting up where we actually have to measure not only can it respond, but what is its, we have to calibrate this thing, so from every single possible angle. So we designed this articulation stage that moves our instrument around like this while we shoot at it with a particle accelerator. So this is me loading up or setting up the articulation stage within a vacuum chamber. And this vacuum chamber is also special because it has this shroud that changes temperatures. So it goes, like I mentioned, from -50 to +50, or I actually don't even know how hot it gets. I was always worried about the cold part. And does the temperature cycles in the vacuum while it's running and getting bombarded with radiation from the particle accelerator. This is our particle accelerator that we had in our lab, and this is really the only way we could test our instrument to see if it worked, because there really aren't sources of the type of thing we wanted to measure just readily available. So it takes quite a bit of effort just to even see that it's working. Any questions? All right, so once you've got it tested and you're really hoping that all your tests worked and that you've thought of every little detail and characterized it and calibrated it in every possible way, then you start to get it ready to go onto the spacecraft. Yes?
Is that still gold that we use?
It is. Is it, oh, do you mean like, is it actual gold? I don't know. It's a good question. I know it's Mylar, but it might be gold-coated Mylar. Actually, I think it is. Yeah. I knew someone would catch me on this. This actually isn't Jedi, because I didn't have a picture of Jedi getting packaged. This is our previous particle detector that's actually the one on its way to Pluto right now. You'll see in a second that Juno actually doesn't use the gold anymore. Thanks a lot. So then you mount it to the spacecraft. Again, this is a picture from the Pluto mission, but same deal. Once it's packaged and ready, it just gets its little home on the spacecraft. All right, so this is this is Juno. So after you're all loaded up there, and you can see the different instruments in their various places around here on the instrument deck. The magnetometer sits right here out on a boom, because you don't want all of the electromagnetic stuff going on in the electronics to affect its measurements. And then this is just a shield, like a sun shield, and then obviously you need to add some solar panels so you can get some power. And one cool thing about Juno is it's the first ever mission to go out that far without using nuclear power. It's actually using solar panels. So it has huge solar panels, and it also meant that our power requirements were really, really high. Like, did any of you guys hear about the Mars mission that just recently launched, a new Mars rover? They have nuclear power, so they, like, you know, they could just put their whole house in there and not have to worry about it. But we had to run our whole instrument off of 2 watts, so. Some people like to go the easy route. I'm just saying. All right.
Real quick question. How heavy is that? It's huge.
Oh, it's a good question. I don't know.
Earth weight, anyways.
Yeah, right. I actually don't know. I might have read that at some point. I know it's 66 feet in span and about 15 feet tall, but I can't remember how much it weighs. Probably a heck of a lot more than you would think because of all the radiation requirements. Like this whole little suitcase here is actually what's called the electronics vault, and it's made out of other really, really heavy metal material to keep out the radiation. And in fact, some of the instruments are actually just not even designed to withstand the radiation because it would have been too costly. It's just known that they're going to peter out after about a month in orbit. So, but ours is scheduled to go the whole way. So, really heavy. Maybe I'll look it up or something after if we have the interweb.
What is the expected lifespan once it's there?
Good question. And I am going to get to that, but it's going to orbit Jupiter for about a year, and it's 33 orbits around Jupiter. So 5 years to get there, 10 years to make, and 1 year to do all its work. All right, so once you've got your spacecraft, well, then what do you need? A rocket. So this is our mission used an Atlas V rocket, and this is them loading it up into the vertical assembly building. Then you take your spacecraft, you fold it up, and you put it in the nose cone. And obviously that's it's all been designed to fit perfectly and everything. And then you take the nose cone and you put it on top of your large explosive rocket. And then it goes into space. So I was fortunate enough to be able to attend the launch. It was launched out of Cape Canaveral in August of this year. And yeah, so those little detectors that we saw way in the beginning are buried in this nose cone somewhere. The nose cone. And then the solar arrays deploy. So they unfold and it gets that shape that you saw in some of the earlier pictures. And as I mentioned, 66 feet. A movie that is just going to describe what happens when the spacecraft gets to Jupiter, and you can see a little bit about what the orbit's going to actually look like once we're there.
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year.
Any questions?
Ooh.
Did you guys get all that?
Wikipedia says 7,990 pounds.
Awesome. Did you hear 7,000 and change?
How many total experiments are on the Earth?
You know, I don't know exactly, but it's something like 10. There's about 10 instruments, but you know, how many different experiments and what's going to be done with that data, it's just going to be never ending. There's going to be papers published about all kinds of nuances for a really long time. This is just this is my final slide, basically to describe the 33 orbits around Jupiter and how they're going to look. It has a highly elliptical polar orbit, and so the idea is that the planners made it so that it wouldn't be in the main radiation belt of Jupiter, so that it could have a longer life, but it needed to get close enough to actually study the auroras at the poles, because that's where everything interesting magnetosphere-wise goes on. So it basically dives into the poles, comes really, really close to the surface of Jupiter, and then goes way, way, way out, and then then does that again. And Jupiter has a really fast rotation, so you can tell that even though our spacecraft going around it is very fast, the planet turns quite a bit in that time. So it had to be designed that by the end of the mission they would have gone over every spot on the surface to be able to map it. So that's why that's what that sort of meant to show. And then after the 33 orbits, we will crash land to Jupiter.
When you're on Earth and you're sending something to Jupiter,
Yeah.
obviously it has to be exactly the right spot to get there and get into the right orbit.
Yep.
Is that all a matter of having it pointed exactly the right way when it?
It is,
off?
and
How much do you steer along the way?
yep, there are mid-flight course corrections. And one of the reasons it's taking so long is they're using what's called like a low power gravity assist type of trajectory. So they're using a lot of flybys to get up speed and to sort of hurl it towards Jupiter. In fact, there's an Earth flyby in 2013. It's actually going to come by Earth again. So yes, it is. It's exact, but they have a little wiggle room along the way. They do course corrections. Yes.
I'm just kind of odd why we're done, so we can crash the thing. Why don't we just leave it going? Or is there some kind of study as it's going down into the atmosphere?
That's a good question. There's not.
It just baffles me that we send something up there that long, all this good technology.
It's both this new field called planetary protection, because there's actually theories of potential life on Europa, the moon Europa of Jupiter. They don't want anything from this spacecraft to get on Europa, because if it did, and then we eventually found life on Europa, people could say, well, that could have been contamination from our spacecraft. So and that's actually a big concern with Mars missions. They actually sterilize everything that goes to Mars before it can go. And there's a whole planetary protection arm in NASA that makes absolutely sure that no bacteria from Earth gets on these places where we're potentially looking for life. So exactly. Yes, you had a question?
Are we
building new spacecrafts for humans?
We are right now, actually. Yep. There's a new mission called the Crew Return Vehicle that's going to bring astronauts between Earth and the International Space Station. Yes.
During the 5-year trip out, is any data being collected?
Great question.
Equipment being tested or anything like that?
Yes. Since you asked, they actually have turned on the subsystem within JEDI that was the subsystem. I worked on the energy detectors, and they are working. Yay! They actually detected some solar storms around Earth, the same ones that caused some pretty big aurora back in October. The science is a little limited. It's mainly just a lot of checkouts, but like for example, one time in the flight where they are going to do science is when they do the Earth flyby. They're actually going to study a little bit about Earth's radiation belts.
And you mentioned at the very beginning that the detectors completely absorb the. Does that mean anything gets destroyed? They have limited lifetime?
They actually rejuvenate themselves, so they don't get destroyed, but if there were different types of radiation that are there, they could actually become destroyed. So that was part of my job, is I actually shot them with lots of different types of radiation, like protons, for example, are really bad for them. And also, not all radiation is fully absorbed. The higher energy stuff just blows right through them, and it deposits just as much as it can on its way through. And so, but yeah, they can deteriorate with certain types and certain energies of radiation, but they will not for this mission. There are other things that have a lower lifetime in terms of the radiation.
One other question.
Yeah.
How much data does this experiment generate?
How much does it generate?
Data.
We can count about 10 million particles per second. But then the data products we make don't give the full information about every particle. So that's why we have all the complex digital electronics, because it actually will generate just sort of a summary packet of data, because we don't have the transmission bandwidth to send back all that information. So it's sort of hard to answer the question how much, but basically, for my instrument anyway, every second we're collecting millions of particles, and we're actually notching every time something like that happens. So, yes.
Personally, I mean, how did it happen that you got involved in this? And also, how is it that you're in Barrow sharing Jupiter stuff with us?
Personally, well, when I was in 5th grade, I had posters of space and Antarctica up on my walls in my bedroom. And so right out of college, I got a job at NASA, and I worked there for a couple years, and then I landed my dream job working at the South Pole. So then I went to work at the South Pole for a while and other places in Antarctica. Then I got this job, so I attempted to work a full-time normal person job, and it lasted a few years, and then I started working in polar regions again. So then I went to Greenland, Antarctica some more, and then, you know, Barrow is just a natural extension of all that. So, yeah.
So what are you doing in Barrow right now?
Oh, I'm working at the NOAA lab. Are you familiar with the NOAA lab, or the, you know,
It used to be CMDL.
Yeah, people refer to it as CMDL. And we do, so we do a lot of more atmospheric science and things like that. So,
So are we going to get to see another Saturday talk on the South Pole?
I knew Knock for about 30 seconds before he asked me to do a Saturday talk.
Thank you.
No, I'd be happy to, I mean, if you want to hear about it. Actually, I have already committed to do one more talk it's very general, but it does highlight a little bit about the work at South Pole.
Are you still have some affiliation with the...
I actually am. I've switched to a part-time, temporary, on-call telecommuter, which is the least committal way you can have a job. But this is my work computer, and yes, I am still affiliated, and they do still occasionally send me questions like, what about those detectors? Can you send us some test data from blah, blah, blah? So, and for a while I was doing a lot more telecommuting, but now that, you know, I have a full-time job here, I don't do as much. But yeah,
Well,
I'm
I
still
guess
affiliated.
specifically when you get to Jupiter, are you more involved then? Back again?
I would say I will become involved if something goes wrong. But amazingly, it's really out of the hands of the engineers once it goes. We have emissions operations specialists. One place where that's not the case is the people who, like I was really involved in a subsystem, but there are also engineers who are more systems engineers that you know, are more aware of the whole operation. And they actually work with the missions people to come up with the command sequences and things like that. So that is one way that instrumentation engineers can be involved after launch, but that's not, I probably won't do much of that. But if they had turned them on a couple months ago and they hadn't been working, I might have gotten a phone call. But instead, you know, it's like business as usual. Yes. Thanks, everybody. You guys are awesome.
Thank you.